The next section of the notes will cover the ways to separate mixtures. So filtering is one process that is allowing us to separate solids from liquids. It works because the solid particles are so large they can get trapped by a piece of filter paper and the liquid goes through the filter paper. There might still be stuff in the liquid, so if you have the particles too small they can actually go through the holes in the filter paper, because on the microscopic level there are holes in the paper that allows the liquid to go through. But if you have large chunks of sand, let's say, in water, you could filter it out. This is how coffee filters work. When you filter out the large pieces of the coffee grinds, you still have a colored liquid when it goes through it. Or when you make tea and you have little Lipton tea bags, you can have the filtrate still has particles in it, but you've blocked out some of the larger pieces. So filtering works because of particle size. That's a physical process of filtering to separate large chunks out of a liquid. Now another way to separate mixtures is the process of distillation. Now distillation is used to separate chemical species by taking advantage of the differential strengths of the intermolecular interactions between and among the components. And a lot of times the distillation process takes advantage of the different vapor pressures of the components of the mixtures. Now vapor pressure relates to the boiling point. So simply put, if you have a solution of two or more liquids being distilled, the boiling points are different because the intermolecular connections between the components of the liquids have different strengths, and so one compound might boil at a different temperature than the other compound, and it makes that separation possible. If you have a solid dissolved in a liquid, you're only going to be boiling the liquid, so you don't need to worry about the vapor pressure of the solid. You only have the vapor pressure of the one liquid. So the intermolecular connections between the molecules are what allows us to distill a substance. The higher intermolecular forces that a liquid will have, the more molecules that tend to stick together. So this actually lowers the amount of vapor that would be produced in the liquid, and so that means the boiling point is going to be higher. So if the molecules are more sticky, you're going to have a higher boiling point. That's simply what the slide expresses. And on the next slide we have a picture of the process. Distillation involves two processes. You first boil the solution, then you have to condense the vapor. The setup for distillation is pretty complex. I do have a distiller in my lab where we can make distilled water, and so I could show you what the apparatus looks like. But you have the solution on the left side in this picture. You boil it, and then the vapor goes through a condensing coil, and then the liquid, or the components would drip on the other side at different times depending on what the temperature is on the left. So if you have a boiling point of one substance at, let's say, 50 degrees Celsius, and then the other substance at, let's say, it's water at 100 degrees Celsius, the first substance would go over through the condenser first, and then there would be a little time gap between when the temperature goes from 50 up to 100, so you'd have to change the containers out to separate the first liquid's boiling point at 50 to the water's boiling point at 100. So there is a time difference between one liquid going through the condenser and the other liquid going through another condenser. This is also how you make booze. So if you have the old moonshiners, they would put corn and sugar and alcohol and yeast, which would actually make the alcohol. It's corn and sugar and the yeast that makes the alcohol on the left side, and you'd heat it up in the still, and then you'd condense out the alcohol on the right side, and then eventually you would maybe have some water that would come over, but the alcohol comes out first and then water comes out second. So that's distillation. This page shows chromatography taking place. This is another separation technique. You've probably seen this in your biology class. A lot of biology classes have the kids separate colored ink. Let's say you have a purple pen and it has different components to the pen color. You can separate it using liquid chromatography or paper chromatography. And so it separates the chemical species because the different dyes are attracted to the paper or to the solvent that it's dipped into, usually some sort of alcohol, and through capillary action the liquid kind of creeps up the paper, and then you get the dyes being carried along with those with that liquid at different speeds, and so it allows the separation to occur. So there's an intermolecular attraction between the liquid and the paper and the dyes, which allows that separation. Now again, there is a animation of this on the internet, so I suggest you look at the website and it goes through what happens with paper chromatography, but it separates the mixtures using a solvent, sometimes water, sometimes alcohol, which carries the solute, which in this case is ink, up a strip of paper, and then it separates it into its component mixtures depending on the amount of the attraction between the ink and the paper, or the ink and the water. Now, another type of chromatography that you're maybe not familiar with is called column chromatography. So it separates the mixtures by pouring it through a column. There's a stationary phase, there's some material packed in this container, and when you pour it through the container, like there's maybe little beads of sand or marbles or asbestos or something in that column, and as the mobile phase is added throughout the process, those different components separate because they're carried through the stationary phase at different rates, because there's different attraction between the stationary phase and the mobile phase. So again, there's a website. You can take a look at the process in more detail, and it's a good animation for you guys to look at if you don't quite understand what happens in column chromatography. Just the basics that we're looking at, not all the fancy stuff about it. This is another picture I found on the internet about column chromatography. So you have a mixture shown at the top of the column, and then as the solution is poured through the column, those components start separating, and then you could have a detector down at the bottom which measures when the components come through. Now, the previous two examples of chromatography involve liquids. Whether it's paper chromatography or column chromatography, you're separating the liquids of a mixture. Well, gas chromatography can separate the components of a mixture that's a liquid or a solid or a gas by vaporizing the mixture. And the column is shown in the middle of the page, and again, there's something packed in that tube where the gas flows through, and you usually have a carrier molecule or a carrier gas, usually helium, that forces the compound vapor or the mixture vapor through that column. And again, the speed at which it goes through the column depends on the interaction with the mixture components and whatever's packed in that column. And then you have a detector which shows the different compounds squirting out after it's gone through the column. So this is called gas chromatography. I have another slide which shows one of the actual gas chromatographs, as they're called, for gasoline on the next slide, so we'll talk about that a little bit. So this is a gas chromatograph of a compound that was put through the machine, and it took 30 minutes to prepare, and as the compounds started to go through, they were separated according to their attraction to whatever it was in the column, and so they're separated. Now, it's important to note that you can't tell the difference between the molecules. I know that they're listed here, like the first one that came through was 3M pentane, and then there's an N heptane that is, sent through. But those identities of the molecules in the peak were figured out in another process, not the gas chromatograph process. So you can put another machine on there to figure out what the actual compounds are, but this just shows that you had a mixture. And so that's what's important about gas chromatography. You can figure out that you have a mixture because the time it takes the gas to go through the column is different depending on the attractions of the component mixtures to whatever is packed in that column. Now we're going to cover stuff that you may or may not be familiar with. It depends on who you had as a chemistry teacher and when you took chemistry. Some teachers cover the topics of precision and accuracy, and others don't. So I don't know who you had for chemistry, but I'm going to cover it like you sort of know what's going on. So what's the difference between precision and accuracy? First, we have precision. It measures how close a set of measurements are to each other. So it could also tell you how specific a measurement is. So for an example, you could list pi to a various amount of precision decimal places. So most of the time you just write 3.14, but we know there's an infinite amount of decimal places, so you could record it to an infinite amount of precision. Sometimes when you're asked how old you are, if you're like 5.5 years old or 18 years old or 50 years old, you kind of round it off to the nearest year, or maybe you round it off to the half year or month or day, or if you know what time of day you're born, you can go down to the minute, but you have a different level of precision when you record how old you are. Now below you can see two measurements of the same object, and they have different amounts of precision. When you're measuring the mass of an object, the number of decimal places will tell you the amount of precision. So we have 54.07, and that's the uncertain digit. Like if you have an electronic balance, it might be flashing between 0.07 and 0.06 or 0.08, but there's some uncertainty in that last digit. And then you have another scale that goes out to like 5 decimal places, so there's more precision when you have those more decimal places showing up. And that's precision. Now, how precise can you measure the volume of liquid in a container? Well, the rule is that you just need to read between the markings and kind of estimate what the volume is. So you can clearly see it's at least 17 milliliters of liquid, but it's between 17 and 18, so we can estimate that extra digit of precision. So when you have a choice over here in the multiple choice, you can have the volume be 17 or 17 and a half, or maybe 17.49 or 50 or 17.500. What is the limit on the precision? Well, we can only estimate one digit. So we know it's definitely 17, so it's 17 point something. So you could call it 17.5 or 17.6 or 17.4, but you can only go to one decimal place for this particular device. So the answer is 17.5 milliliters. So the rule is read in between the marks, and you can only estimate that last digit of uncertainty. Here's another example if you didn't get it on the previous slide. What is the length of that bar? Well, we know it's definitely 3 centimeters long. We know it's definitely 3.2 centimeters long. It's a little bit more than 3.2, so we could call it 3.2 something. So 3.22, 3.33. It doesn't look like it's 3.35, so you got some choices, but you have 2 decimal places in this case. So it's 3.22 or 3.23 or 3.24, but we're limited by the number of marks on this ruler. So again, the rule is read in between the marks and you get to estimate that last digit of uncertainty. So we're recording the precision to 2 decimal places in this case. Now we get to talk about something called significant figures. Some of you may have had it, some of you may have not had it. But anyway, what is a significant figure? Well, a significant figure, or sometimes called sig figs, or significant digits in some textbooks. Anyway, it's used to indicate the precision of a measurement. So we know how to correctly estimate in between the markings of, let's say, a ruler, as our previous example showed, to record the precision of the measurement to the correct number of decimal places. But if you're looking at somebody else's measurement, you need to be able to tell what the precision of their measurements are. So you count something called sig figs. So the number of significant figures in a measurement is the number of digits that you know for certain plus one uncertain digit. That's the estimated digit that's maybe between the 2 markings on a ruler or something like that. Or if you're rounding off pi, it's 3.14, but you kind of rounded it off to the 3.14, the second decimal place. So the significant figures is recording all the digits you know for sure, plus 1 that's uncertain. Now here's an example. You have 2.2405 grams. So if somebody measured this on a balance, we know all the digits for sure are the 2.240, and there's an uncertain digit of the last 5. So you know the 2.240 for certain, and there's some uncertainty about the last digit. So if you want to say what the precision is, we would say it has 5 significant digits. 4 you know for sure, 1 that's uncertain, but it still counts towards the precision. So we say there's 5 significant figures in that measurement. So the scale is very precise. Now, if you're measuring something, there's uncertainty. But if you're just counting the number of objects, let's say you have 7 pencils that's in your backpack, you're not estimating how many pencils are. You can physically count up to 7. So we say that the precision is to an infinite amount of precision. So it's not like you're rounding it off. So we say that the precision is an infinite amount of significant figures, or an infinite amount of precision. So some conversion factors have an infinite amount of sig figs because you know them exactly. They're not rounded off. For example, here's some that are known for exactly. So 60 seconds is exactly 1 minute. 2.54 centimeters happens to be exactly 1 inch. That is not rounded, though it looks like it is. It is not. 1 meter is exactly 1,000 millimeters. All of those measurements have an infinite amount of precision because we're actually counting how many seconds are in a minute. We're counting how many millimeters are in a meter. It just happens that 1 inch is exactly 2.54 centimeters. Probably somebody wanted to define an inch as a very exact amount of centimeters. That's not rounded. Now, how many days are in a month? It's either 30 or 31. That can be rounded off. a little bit. You could figure out how many days are in a year. It's 365, maybe it's 366. You got to round that off. It's actually 365.25. That's why they have a leap year. So some measurements you have to actually measure or round off. You have to estimate, but others are non-exact. We're talking about exact measurements, no rounding involved. You're basically counting. That's an infinite amount of sig figs. Now there's a strategy that I've discovered from the internet on how to count the number of sig figs in a measurement. Now this is a measurement that somebody else has given you. So they're measuring the length of a piece of paper or something like that, or maybe how far they drove in their car. They're just recording a value, they've rounded it off, and you're looking at it. So the way to count number of sig figs, you could follow some rules that maybe a teacher has taught you in the past, or maybe I've taught you in the past, but the heck with that. This is a much better method for counting the number of significant digits or significant figures in a measurement that you're looking at. So here we have a measurement. It's 0.0020530 meters. What are the digits that are known for sure? What are the digits that is the estimated uncertain digit? Well, the method that we use is called the box and dot method. So the dot refers to the decimal point. So here's the process. Very easy to figure out. Step one, you're to draw a box around all the non-zero digits, beginning with the one on the left side and continuing to the rightmost. So we're going to put a box around anything that's not a zero, and that includes zeros that are in between the digits. So we'll circle the 2, 0, 5, and the 3. So that's the box around the 2053. That's the far left non-zero number and the far right non-zero number. Now, this measurement now has at least 4 significant digits because there's a box around them. How do you figure out if the zeros count or don't count towards the precision? Well, if you see a dot, continue your box to the right. So continue adding a box to any zero that's trailing the number. So again, that's the ones on the end, the right side, not the beginning ones, the trailing zeros. So we'll add a box around that zero. So if you see a dot, draw a box around the zero on the far right. That also counts towards the precision. So you just count how many digits are in the boxes, and that's the number of sig figs. There happens to be 5 in this measurement. Now we're going to do more practice problems on the next slide, so get ready to rock and roll. So using this concept of the box dot method, we're going to count the number of sig figs in these 12 examples. For practice problem number 1, you'd put a box around all 4 values right off the bat. There isn't a decimal point. You just circle them all and you're good to go. So there's 4 sig figs in the first example. In the second example, there's clearly 3. In the third example, it's just like the first example, there's going to be 4. In the fourth example, there's going to be 4. The zeros at the beginning don't count. Now, number 5, it's written in scientific notation. Nobody cares about the 10 to the 5th power. When you're looking at sig figs, it's just the 4.6. They both count towards the precision. That means there's 2 sig figs. Number 6, you put a box around the 406 and you're done. For number 7, we have the first time where there's like a choice. You'd put a box around the 75. Now, do you put a box around the 0 in 750? The answer is no, because you didn't see a dot. If there's no dot, you don't put a box. So there's only 2 sig figs in 750 liters. They measure the precision to the nearest 10 liters. You don't know it down to the ones place. They rounded it off. We're just looking at somebody else's measurement. 750 liters has been rounded off to the tens place. Now in number 8, we have a bunch of zeros and then 750. Do you put a box around that last zero? The answer is yes. You see a dot, you put a box around the last zero. For number 9, it's 75,000 seconds. Do you put a box around the zeros? No. You don't see a dot, you see a comma. That doesn't count. There's only 2 sig figs in 75,000 seconds. How about 75.00? Well, I see the dot. You can put a box around the zeros and obviously the box around the 75. So there's 4 sig figs in 75.00 meters. In example number 11, I see a dot. I got to put a box around all the zeros at the end. Now that is going to make all the zeros count. If there's a box around the 75 and you see a dot, you just keep drawing the box around all the zeros to the right. So that's 6 significant figures. That's an extremely high number of sig figs. That scale is very precise. It can read up to, what is that? Up to the 10,000 number of grams down to 1 decimal place. That's pretty unusual. Now the last example is 10 centimeters. Well, obviously the 1 counts as a sig fig. Since I don't see a dot and the 0 doesn't get a box, so there's only 1 sig fig in the last example. If you don't catch on to the sig figs at this time, that's okay. We're going to do it briefly on the next slide as well. Now, in the vast scheme of things, significant figures aren't majorly important on the AP exam. The only time they come into play is when you're going to round off your final answer. So generally speaking, on the AP exam, you should probably round off your answer to 3 sig figs, but there are rules to follow. Now, the reason I say 3 sig figs is because they usually give values in experimental measurements around 3 sig figs, and if you're off by just one, like if you're supposed to record 3 sig figs but you rounded it too much and you only recorded 2 sig figs, they're not going to take off any points. Or if you put down 4, which is one more than you're supposed to put down, they're not going to take off any points. So I usually just tell the kids, hey, if you don't know what you're doing for sig figs, just round off to 3 sig figs and you're good to go. But anyway, there are rules to follow. So you only have to round off your final calculation. And you only record the precision of your final answer to the least significant measurement. So you look at the precision of all the measurements that you take and you round off to the one that's the least significant measurement. Now, there's 2 types of calculations you do, and so there's 2 different rounding rules. If you multiply or divide, you just count how many sig figs are in the values and you round off to the least number. So here's an example. You have 4 sig figs in the first measurement, you have only 2 sig figs in your second measurement. So when you're multiplying these together, you can only keep 2 sig figs in your final answer. So you have to round it off just to 32. I know there's a bunch of decimal places after that, but you got to round it off only to 2 significant figures. So 32 square centimeters is going to be your final answer. Now, if you're adding or subtracting, it counts as the decimal places where you round off. So you just look at how many decimal places are the least amount, and you stop there. So in these values of masses that are going to be subtracted from each other, the first measurement only has 1 decimal place of precision, the next one only has 3 decimal places, so the first one has the least amount of decimal places. So no matter what your calculator shows, when you subtract these measurements, you can only keep 1 decimal place. So you're going to have to round it off to 19.1 grams. So that's your rounding rules. Learn them. Now we'll talk about accuracy and then throw them all together so you'll know the difference between precision and accuracy. Accuracy is how close your answer is to the right answer, how close you are to the accepted value. If you take a group of measurements, you can take an average and compare your average to the accepted value, but that's accuracy. Now, a percent error is a way to calculate how accurate you were. Percent error is a simple calculation. You just subtract your answer from what it was supposed to be, and you can take the absolute value of that, and then you're going to divide by what the accepted value is. We're going to do some practice problems on percent error. I'll give you 1 or 2, but it's a very straightforward formula. If you've taken physics, you have to do percent error a lot, so it's a simple formula to use, and you need to learn it. Oh, and you need to express it as a percent, so you need to multiply by 100 when you're done. Now this is a classic slide to see if somebody knows the difference between accuracy and precision. So I want you to describe the targets with the words precise and accurate. So the first target in the top left corner is both. You're shooting where you're supposed to be shooting for, they're all close together, so it's both accurate and precise. Now what's the next target? Well, we have 5 shots. If you were to average all the shots, you would still be in the bullseye section. So we would say that it is accurate, but since the shots are far apart from one another, it's not precise. So that's accuracy without precision. So they kind of got lucky. They kind of got 5 shots kind of all over the place. You know, 1 is in the middle, but the other 4 average to still be in the middle. So that's accuracy without precision. What's the third target in the bottom left? Well, this has good precision because they're close together, but they're not accurate because they're not hitting the bullseye. And the last one you don't have either. The shots are way off, the average is way off. There's no precision and no accuracy. Finally, we have the last topic in Unit 1. It's called density. You've seen this formula before. It's mass divided by volume. And I use something called the density triangle for people that hate algebra. So if you write the formula in this little triangle, you can see if you want to solve for the mass of the object, you can just take the density times the volume of the object. Now if you're doing the density of liquids, it's usually grams and milliliters for your mass and volume units, or grams and cubic centimeters. If you're doing gases, though, you need a lot of gas to get a significant amount of mass on a scale. So they usually do the grams for the mass unit, but like liters of gas for the volume unit. So that's the density. Now what does density tell us? Well, it determines if something will sink or float in another substance. So if something sinks or floats in water, it has a density greater than or less than 1. If it sinks or floats in air, it has a density greater than or less than the density of air, which is around 1.2 or something like that. So if it's more dense, it's going to sink in the substance. If it's less dense, it floats. If they have the same densities, it's going to hover somewhere in the middle. And the reason a helium balloon can float in air is because the helium is less dense than air. A lot of people say that helium is lighter than air. Well, lighter describes the mass. It's not the mass of the helium that's lighter than air, it's the density of helium that's less than air. So be careful with your terminology. You'll hear people say, you know, if it's lighter than air, it floats, but it's less dense than air is the proper chemistry way of describing it. And density can be used as a conversion factor. It's a ratio of units that are equivalent to one another. So 1 gram of water is equal to 1 milliliter of water at 4 degrees Celsius. That's where water is most dense. But you can use the conversion of grams to milliliters by setting that ratio of equivalent units equal to one another. So here's another example. The mass of 1 mole of helium is 4 grams, and that volume would be 22.4 liters of helium when you're at standard temperature and pressure. That's called STP. You might remember that from first year of chemistry. But you could set 4 grams of helium equal to 22.4 liters of helium because that mass and volume are equivalent measurements of a quantity of helium. So you can use density as a conversion factor, and we'll practice some more conversion factors in class, but not officially in the PowerPoint. So that finishes Unit 1.